Now, all right, so we went over grades, so Schoology. We know some people are having trouble logging in. We talked about going into the active, you should be taking notes, right? Active Directory. Through the CMSD portal. Do not go into Clever directly. Go into login through the CMSD, then Clever. Mr. Mendoza's room. Hello? Okay. Then Clever, then go into Active Directory. That should, according to Ms. Perez, correct most issues. Anything else, you have to go to Ms. Perez, go to Dr. Adams. You have advisory, do you not? Everyone in here has advisory? Okay, with Dr. Adams? With who? All right, so all of you that have advisory, whether it be Porter, Krupa, or Adams, see them about this. The other thing I want to talk to you about Schoology when you're turning things in is do it using PDFs. It'll save you a lot of trouble. You'll have the ability when the teacher opens it, they see all your work. Not just if they don't. If you turn it as a picture, I've had several people turn in pictures. I can't open the format for whatever reason. Schoology can't open it. I download it and I try to open it. It gives me an error. I don't know what kind of picture was uploaded. I don't know how that happened. If you save it as a PDF, it's universal. I've shown you how to do it. If you want to see me during lunch or after school, I can show you again. No matter what your technology, we can probably figure out how to do it with a PDF. All right, so that's Schoology. Grades, we talked about grades. Guys, I said it before, I'll say it again. All you got to do is turn it in. On time. I want to give you a break. I want to say I'll give you till Tuesday night to get it all turned in for full credit. What's the problem with that? Does anybody see a problem with me saying that? What's the problem with me telling you I'll give you till Tuesday night to turn anything in that's late and I won't take any points off? It was already due. You should have done it. That's true. But why would it bother me to do that? Why would it bother me like I don't know, let's say this young lady's missing work and it's like I give her an extra couple days to turn in, fix whatever problems. What's the big deal? Can anybody see a problem with that? I mean, I do. That's why I'm not doing it, obviously. But do you see a problem with it? It encourages procrastination. It encourages, part of the problem you guys had, not you personally, but a lot of students had during the COVID time when we were virtual, is you guys procrastinated, right? You held back, you didn't do, and then you felt overwhelmed, right? Remember that? Do you remember that feeling? Yes? I mean, did that not happen to you? We're not going to talk at all? No communication? No, it didn't happen to you at all? You kept up with everything all throughout the virtual time? Everybody did here? Okay, so who didn't? Who did not? Raise your hand. Be honest, because it's not going to hurt you anyway. It threw a lot of people off. And let me tell you right now, I'm not going to encourage that behavior, right? I'm not going to encourage that because I think and when I see your class isn't as bad off. I have a class where half the kids have nothing turned in. And that's not acceptable. I guess that's where all the kids that had trouble during the virtual days, I guess that's where they all are, is in that other class. I don't understand. You're doing work. These last couple weeks, this beginning, this intro to biology was just work in class. There was just all classwork. There were notes. They were easy quizzes. And I can say that with certainty because 100% of the people that turned in got 100%. They were just practice for the big game. The big game starts today. Like it should have started last week, but we're starting today. So easy quizzes, notes, just work in class, upload it. And you had days and days and days of extra time to get it turned in. Now, that being said, there were some technical issues that some people might have had. So there were 3 technical issues. I've heard of at least 3 of them right now in class, before class even started. So these tech issues, get them resolved. Again, I say Perez, advisory, I thought Dr. Adams had all the 9th grade advisory, all the 9th grade students, but I guess not. Perez, advisory, but get them resolved. And secondly, see me, talk to me. I'm more than willing to give you extensions to talk to you about it. If I can verify that you had technical issues, that you had real reasons why these things didn't happen. Those of you with tardy passes, could you put them over here? Thank you. So you have to see me and talk to me if I can work with you if I know what's going on. I can't work if you have a problem, if you have a question about an assignment like the one the young lady, remind me your name, dear. Like Amadi said today, hey, these 2 assignments were the same. Well, they weren't, but she didn't notice that they weren't. So a question would be helpful, right? A conversation. Raise your hand in class. Say, Mr. Mendoza, these 2 assignments are the same. Guys, no jean jackets. Notebooks should be out. Check your Schoology. All right? I shouldn't have to stop class when you're coming in 20 minutes late to explain that, but that's okay. All right, so see me and talk to me. I will be calling home. And that's the 4th thing I want to say before we move on. I will be calling home with anyone missing any work. If you're missing any work, I'm calling home all this week. I'm going to start with the lowest grades and move up. So at some point, I will get a hold of your parents.
Missing home?
Sorry. My bad. I'll be calling home for missing work. There should be no missing work. All of it's done in class. If you're missing work, what does that tell me? You're not doing anything in class. That's not acceptable. You're just sitting there pretending to do work in class, and that's not okay. Yes. Yes, please, go ahead, turn on. I would ask you to turn half the lights off, see if it works. If not, turn the other one off. Yeah. No, I turned them back. I told you to upload them. Yeah, you had to take a picture and upload them. Everything got turned back. Because remember, people didn't put their names on it. They didn't put their periods. Everything got submitted back to you. Anything that you did turn in. But any individual questions, again, what are you going to do? See me. We can talk about it, but not now because we have to get on with class. All right, so I'm willing to listen to you. We can talk about it. Let's talk about it and resolve any issues. But at the end of the day today, actually throughout the day, because I have some unassigned time I'm going to dedicate just to contacting parents whose students have a great deal of missing work, because I can't just let that go by. You know, your parents are going to ask me, why didn't you tell me this was happening? They're in your class. I can't be in your class with you. Like, I can quote your parents before they even say it because I've heard it so many times. So I will contact and I will record that I contacted your folks, and we'll continue, and at some point somebody's going to get a hold of a parent. So here's the solution to resolve that before it happens. Turn in the work. Turn in on time, but no matter what, turn in. And talk to me if there's any issues. Talk to me before we get to the point where grades are being turned in. You understand interim progress reports are coming up. Like this quick, you're going to get in danger of failing. That's how close. I think the grades are due next month. Did you know grades are due next month? Just that quick. So I don't know what to say. You got to turn the work in. You got to turn on time. There's absolutely no way around that. All right, so let's go on with class, and let's talk about what we have to talk about. Where do we leave off in this class? Who knows? Who has notes that knows where we left off in this class? I see spiral notebooks that are not in binders. I'm wondering if you understand, again, a binder is required. You need to take your handouts. You need to have everything in place by date. And I really suggest leave loose leaf notes in the binder. But if you're going to insist on spiral notebooks, you have to have everything in by date, including handouts. All right, so where do we leave off according to the notes? We talked about atoms or something. Covalent bonds, okay. Ionic bonds, all right. Well, we did a lab. Lab 1 was on pH. That had to do with covalent, that had to do with a chemical reaction. And that was on Thursday, that's right. That's another set of grades I'm going to put in. I haven't even looked at Thursday's grades yet. And how do you guys like having two Schoology places to go for one for the lab and one for class? Do you like that, or would you rather just go to one place?
Yeah, just one. It gets confusing.
All right, you don't have to explain. I'm okay with it. Here's what I'm going to do. I'm going to transfer all the grades over to one place, and I'll get rid of the second one. I can't get rid of it, but I'll put it off and say, do not use this site. The problem you're going to have, though, is I really don't think that's as good as a collegiate experience as you would have in college, but I'm okay with that. If it's going to make your life simpler, that's fine for me. So chemical reaction. And then we have covalent bonds. We talked about covalent bonds and ionic bonds. There was also, the lab also had to do with indicators. And you had this idea of moles and this idea of concentration in moles per liter. And what I'm doing here is reviewing. This is what reviewing looks like. When someone comes in to me and tells me and I ask them, look in your notes and tell me what you did last week, what do we leave off? And somebody says to me, ionic bonds, covalent bonds. I'm like, are you really reviewing? Are you reflecting? Are you reciting? Are you looking at your notes for 15 minutes a night every night? I don't give you homework every night. That's what I'm asking myself when I hear you answer these questions, right? And I know what the answers are. So you need to see that this is why I tell you to do these things, because you're not going to be prepared otherwise. You're literally not going to be prepared. And then you're going to complain that you did poorly on the test. So I want to be clear. You have to review. You have to recite. You have to reflect. You have to have conversations. What did we cover? What were the important ideas? I ask you to summarize. Why? Because you should be able to come in today without giggling and smiling at me, especially if you came in late. You should be able to come in today and be able to tell me where we are and what we're doing. You should know what we're learning, and you should know where we're going. You should have questions for me. You should have questions over the lab we did. You should have questions over the content. If I gave you a test over the stuff we did last week right now, I said, I'm going to give you a 20-question test. Could you handle it? No. No, you couldn't. And I'll be honest, you're coming in 20 minutes. Some of you are coming in 20 minutes late. You're missing 20 minutes of content. Some of you are not taking good notes. You're not turning stuff in. Oh, excuse me, 27 minutes late. You're not getting things done. You're not turning it in. You're not reflecting. You're not reviewing. And then what do you expect is going to happen? I just want to know what the expectation is here. I really want to know, what do you expect is going to happen? Young man, did you... I forgot your name. I'm sorry. Yeah. Jacob, do you have a tardy pass? Could I have it, please? So what do you guys think is going to happen when you get a test? Thank you. Like, what do you think? It's not funny to me, because I know the outcome. I know the outcome's not going to be good. And I know it's not about me. And let's be clear, this is not my work. This is your work. So if you're not reviewing, reciting, and reflecting, and don't tell me that you have work for other classes. Don't let those words come out of your lips. Because I haven't assigned you any homework except at your leisure read 2 chapters. And you have time to do that. And take notes in class. Is that too much to ask from a high school student? I don't think that's too much. And upload it to Schoology. I'm not asking too much. And you guys are not doing it. What do you think is going to happen when you take the test? You're going to fail. Or at least not do as good as you want. What kind of conversation am I going to have with your parents about this? Ma'am, your daughter, your son is coming in 20 minutes, 27 minutes late regularly. They're not turning work in. The work, they don't know where we are in the curriculum. They're not reflecting. They're not reviewing. They're not, the word is studying. They think they're in middle school when they're in high school. They think they're taking a middle school class instead of an honors biology class at the Cleveland School of Science and Medicine. I don't know. I'm not trying to stress you out. I'm trying to wake you guys up. Because I don't see, and I'm recording all this, and I'll be sending it to your folks as well. So I want to be clear that there's not going to be any miscommunication over what the problem here is. Okay? So we need to correct these things. It's not too late. It's not an emergency. You haven't missed anything you can't fix. We're not so far down the rabbit hole that we can't do some self-correction, some reflection, and correct the problems. There's nothing that can't be fixed with a conversation and a change in behavior. Is that correct? Is that understood? That's where we're at right now. My concern is that if we keep going, we're going to get to a point where it's not going to be repairable, at least as easily repairable. And then we're dealing with report cards and grades. And I don't want that to get to that point. Because grades are important to you. Is that correct? They're important to your parents. Report cards, transcripts, all that. So don't tell me they're important to you in a month when the grade report cards are coming out and then not do anything about it today. Right? Don't tell me that grades are important to you, that you needed to get into college, into an internship, into whatever, but then not do anything on a daily basis to fix the problem. And I do, as I said before you all came in, I understand that there's a long line out front and they're trying to resolve that. But that just means you guys have to adapt, right? And I understand that you sometimes don't have control over that. But you know what you guys need to do? You need to come and talk to me. We need to have a conversation over what's going on, why you're coming in late, so that I understand. Because I'm your teacher. And maybe, guess what? Maybe I can help you. So you need to talk to me. Is that clear? All of you that came in late? Yes? Okay, talk to me. Come during lunch. Come after school. Sit down, have a conversation. We'll make some tea. We'll have a conversation on what the heck is going on and how can we fix it. All right. And believe me, there are ways. This is not the first time in 24 years that people have had trouble coming to class on time. There are ways of fixing it. All right. So we did talk about these things. If you don't understand any of these words, if any of these words look like they're strange to you, well, that should be a flag. That should be something where you need to, that's part of reflection. That's what reflection means. Is I don't understand. That's where the questions get written here in the cues. I don't understand what moles are. I don't understand what concentration is. I don't understand what chemical reactions are. What's the difference between chemical versus physical reactions? What is the difference, or physical changes? Chemical changes versus physical changes. What are those things? What are concentrations? What are hydrogen ions? Another thing we talked about. And what do they have to do with pH? Those are all questions you should, if I gave you a test today, you theoretically should be able to pass that test. All this is covered in your book. All this is covered in some of your asynchronous work. So it should be a pretty straightforward, and also in class we discussed it. And you took notes on it. And yes, this is a quick reflection / review. Do you understand covalent bonds and the difference between covalent and ionic bonds? Do you understand the idea of polar covalent bonds? Look at how much stuff we covered in 1 week. And why it's important to me that I know that you're writing it down and that you understand. All right. So we talked about things, and of course we talked about water. And today we're going to go a little bit more into water and polar covalent bonds. So at any point in this discussion, if you hear something you don't understand or you'd like clarification on, the best way you can handle that is to raise your hand and say, Mr. Mendoza, I don't understand that. And if it's going to take too much off track of where I'd like to go today, I'll ask you to hold off a second, or see me after class, or let's make an appointment during lunch, and we'll go into detail on that. So I'm here to explain things to you. I'm not here to check and see if you memorize something. I'm here to explain to you and teach you what you need to know. That's why I'm here. But I can't teach you if you don't ask questions, if you don't cooperate, if you don't participate. Does that make sense? All right. So, review. And I'll have a quiz for you tomorrow on this content you see here. And so that quiz will be an opportunity for you to see if to help you answer this question. To answer this reflect and review, right? What is it that I don't understand? So tomorrow's quiz is an opportunity for you to figure out what is it that I need to focus on. Maybe I don't understand polar covalent bonds. Maybe I don't understand concentration. Maybe I don't understand what moles per liter means. Maybe I don't know what an indicator is. Maybe I don't know what chemical reactions are. Maybe I don't know what covalent versus ionic bonds are. Whatever it is, there's going to be a quiz on these topics. And pH, don't forget pH and hydrogen ion concentration. By the way, I posted the videos on Schoology already of the previous classes. So if you came in late, one possible quick solution is to watch those videos and catch up on any content that you missed. Because trust me, we start at 8 o'clock. So you're coming at 8:20, we've already covered 20 minutes of stuff. I don't know what that is. It could mean me just talking about Schoology, right? Or it could mean me explaining something. I don't know. All right. So let's talk for a second about, let's go back for a minute and talk about this molecule water. What is a molecule? Molecule. It's a simple word. You please, refer your notes if you have your notes on it. And this is where an organized notebook that has good headers and cues can get you. Because if you have Cornell notes, you have the word molecule on the left-hand side. You probably highlight it because it's an important word, and you can easily scan and identify. Why are you not taking notes, young man? What's the problem? I can't hear you. You're the only one I see that's not taking notes, or at least doesn't have something out. In the entire class, you're the only one. You're asking me, am I talking to you? Yeah.
Molecules are strong relationships between atoms.
Strong relationships between atoms. That's right. That's good. That's good. It's a group of atoms. Let me be clear. It's a group of atoms that share electrons. In other words, they have a strong relationship. They're a group of atoms that have a strong relationship. Somebody have a question? I saw someone's hand go up. No? My mistake? All right. So these lines, do you see these lines here? These lines mean the sharing electrons. All right. So if you think about two electrons and they're going to get shared, what's the shortest distance between 2 points? It's, if these two are the points, it's a line. So a line just means that they're sharing electrons. Anytime you see a molecule, you're going to see some really complicated molecules. You're going to see some really complicated molecules. No matter how complicated it is, each line is just a pair of shared electrons, a bond, a link between atoms. Very strong relationship. So water has a strong relationship, and they're sharing electrons. They're not taking or giving, just like the asynchronous activity should have reviewed with you. But even though they're sharing, they're not sharing evenly. So it turns out that water has this partial positive charge on this side and a partial negative charge on the other side. So there's this positive side on. Let me do two different colors that might help you see the difference. and there's a partial negative side on this side. So this is positive here. So this side has a positive, oops. This has this positive side. So this side's positive and this side's negative. Like magnets, we call this poles. This is a negative pole and this is a positive pole. Two poles. So what do positives and negatives do to each other? Attract. It's just that simple. And so when you have a bunch of these water molecules together, the positive and negative sides line up. They're horrible drawings, I apologize. Now, there's two things that are going on here. Everything in the universe is in motion all the time. Nothing's ever still. So these atoms are vibrating and they're rolling around. That's what being liquid means. When you see liquid water, what that means is that it has a lot of what's called kinetic energy. You've learned about kinetic energy, did you not? So kinetic energy means that these molecules are moving in one direction or the other. So they're zipping that way, they're zooping that way, they're turning around in circles. They're moving and swirling and doing all kinds of things. That's why these things are known as liquids, because they're moving a lot. In which phase of matter do things move even more? In gas. So in a gas, they move a lot more. They have a lot more kinetic energy. Kinetic energy in a gas is higher than kinetic energy in a liquid. And in a liquid, they're moving around and they swirl and they flow. So they have high kinetic energy in a liquid, just not as high as in a gas. And where do they have the lowest kinetic energy? A solid, that's correct. So in solids, you have the least amount of kinetic energy. That's why they're solid, but they're still, of course, molecules of water. They're still the same water. It's still the same molecules. It's just they're further spread. They spread apart more. They're moving less, and they're more organized because of it. So in the solid form of water, in solids versus liquids versus gases, it's the kinetic energy. Having more kinetic energy means the same number of molecules in greater space. So gases, they're moving around like maniacs and creating pressure as they hit the sides of the containers. And they're bouncing around like billiard balls on a pool table. So when you're talking about, there's two different forces that are happening here. Two. The kinetic energy of these molecules would have them flowing around, would have them moving and jumping. But the polar bonds, these polar attractions, these positive and negative attractions, would have them pull towards each other. So they're pulling towards each other, but they're also pulling away from each other because the kinetic energy is pushing them away. So they're at a tug of war, a constant tug of war. Sort of like you're constantly being pulled down to the ground. And you take your eyes off the ball, what happens to you? You're constantly being pulled down, you don't pay attention, what happens to you? You fall. That's what tripping is. You're not paying attention. No one's pushed you. You're falling down because you didn't pay attention and you didn't keep your feet under you. Because if you let it, gravity will pull you down, won't it? Yes? So you need to put energy into not falling. So it's the same thing here. Just like there's two different forces happening with you, there's two different forces happening with every molecule in the universe. In this case, we're not talking about gravity. We're talking about these two forces. One is this kinetic energy is moving things around, wants things to turn. The kinetic energy of these molecules has them flowing and rolling and flying around in their containers. And then there's this pulling together. So when the kinetic energy gets low enough, things turn into a solid. And with most solids, what happens is you put a solid, let's say iron. Let's look at iron, for instance. I take an iron cube and I put it into water, let me put it another way. I put it into liquid iron. What happens to that cube, that solid cube? If I put that solid iron, I'm going to put Fe because that's a symbol for iron, and it's solid, and I put it in liquid iron. What happens to that iron? It sinks. It goes right to the bottom because this is solids are closer together. They are more dense. Does that make sense to you? Tell me yes, no, I can't see you.
Yeah.
All right. That's how we experience life. And that makes sense to us, right? Water, though, it does something really weird. And you don't notice it because you see it happen every day. You depend on it. So you don't really think much of it. It's not a big deal. It's normal to you. But it's not normal. It's something that very, very few molecules in the whole universe do. Very, very few molecules do this. If you look at water and you take a cube of water and you put a cube of water into liquid water, that's solid water. Solid H2O. And you put it in liquid H2O. What does it do? It floats. Yeah, it's ice. Yeah, ice floats. That makes no sense. How does that make any sense? Solids are more dense. They're closer together. They're not moving as much. Their kinetic energy is lower. That's why it's colder. By the way, you should know this. You should know this, and I will test it. Temperature is a measurement of average kinetic energy. See, that makes sense. This fact makes absolute sense if you think about it. If you think about it, the fact that temperature is a measurement of kinetic energy makes absolute sense because then as things get colder, they have less movement, so they settle down. And they go from this crazy gas to this less crazy liquid to this really calm solid. And so the particles that make them up are much closer together. And therefore they're more dense. Well, that makes sense to all of us, doesn't it?
Yes.
But this doesn't make sense. This thing that water's doing makes no sense. Unless you think about this other force that most of these other molecules don't have to deal with. Iron does not have to deal with this other force. But water has to deal with it. What force am I talking about?
What'd you say?
What force? So right now, so far, the only thing we've talked about is kinetic energy, that average movement. And as we slow things down and things turn into solids, they slow down, they get packed closer together, and they become more dense, and they fall in their liquid form. If you put a solid iron in liquid iron, it falls to the bottom of the container. That is correct. So then the question becomes, why is it that ice floats then? Why is ice floating if that's what's happening? What's going on? Why is ice floating if that's what's happening?
Because ice has a lower temperature.
That's right. Ice has a lower temperature, so it's turned into a solid. So it went from a liquid to a solid, correct?
Mm-hmm.
But shouldn't that be denser? Shouldn't it? Then why is it floating? You see the problem? This is a dilemma. This is a real dilemma. Where are your notes? For today?
No, I'm just gonna wait until after class.
Oh, are you? I don't want you to. I want you to sit down at a table and I want you to take notes. It's kind of what I'm requiring you to do today. Today and every day. So when we have here ice floating, there's only the trick is this. The trick is that oops. I still got. Sorry about that. What does the screen look like?
Oh, now it's going to
All right. So water floats because of this. Because when the molecules of water get close to one another, unlike other molecules, they attract each other. There's this constant attraction I told you about because they're polar, because they have a positive side and negative side, right? Because they have this negative side and they have this positive side, the positive and negative, they attract each other. And they line up. That lining up spreads them out. That lining up spreads them out. See, normally that lining up would not spread them out. They wouldn't line up. They would just ball up and as close as they can get. But they can't do that because every time this positive gets close to this positive, what does it do? They repel each other. So they can't get that close. These positives need a negative in between them or they're going to push away from each other. And so they have to line up, they spread out like a snowflake. They spread out. That's why ice floats. It's less dense because we call this hydrogen bonding. This positive and negative force is called hydrogen bonding. And this hydrogen bonding creates this less dense solid. And it looks like we're done with class, so tomorrow we'll discuss why that's important, and there'll be a quiz on all that stuff that we've talked about up to this point. Oh, I just record this, and I'll post the whole thing as one video. So hydrogen bonding is this pull, this force that's happening in between the hydrogen and the oxygen. They're pulling towards each other. It's an intermolecular force. Intermolecular force. And very much the other force that's happening here are these forces here that are intramolecular. Those are the forces that are inside. This means inside the molecule, and this inter means in between. And so the intermolecular forces are the forces in between the molecules, and the intramolecular forces are forces holding the molecule together. It says this intermolecular force is very weak. Not weak as in that, but weak as in this. Very weak compared to the intramolecular force is very strong. So that's going to become important when we talk about DNA and proteins. So you have to understand that the forces, the hydrogen bonding that pulls and yanks and helps shape things is weak compared to the force that's holding the atoms together. So it's a really important idea there. All right, that being said, this pulling together of molecules allows for water to float. So, average kinetic energy, right? Average kinetic energy is the average energy of motion. So, here you have this water molecule, and they're horribly drawn. I apologize ahead of time for this, but I'm doing it quickly because we don't have a lot of time. So here's another water molecule here. Another horribly drawn molecule. Another one over here. Now, what do you think is going to happen? So they're kind of aligning. Maybe they're solid. Let's call this a solid. This is ice. And then I take ice and I add flame. I add heat. What is heat? Heat is energy. I'm adding energy. Energy is what, by the way, do you know what the definition of energy is? A definition of energy. It's the stuff that allows for motion. It's the stuff that allows for movement. Without energy, there's no movement. That's just a really strange thing to say, but we'll just say that. Energy allows for movement. It allows movement. So if you know that, that's a really good, quick definition. Energy allows movement. And kinetic energy is the measurement of average movement. Kinetic energy is it. So if I'm adding heat, which is a form of energy, to these molecules that, since they're ice, they're solid, they have low kinetic energy, right? Compared, remember we said that a minute ago? Yes, no, maybe? So they have low kinetic energy, and I'm adding heat. What do you think's happening to that kinetic energy? It's increasing. So they start to vibrate. It looks like we're done since people are putting away stuff. Is it right? We're done? All right, so we'll finish this tomorrow. As you add heat, the movement of the molecules start to increase. And they move faster and faster. And as they move faster and faster, these water molecules start to separate, start to move closer, maybe where they used to be in ice, separated because of hydrogen bonding, forcing them to be in a particular structure. Now with that kinetic energy, this molecule will go ahead and squeeze in this spot. So it becomes denser, it becomes more fluid, and it turns into a liquid. Keep adding heat, and it'll turn into a gas. All right. So that's the idea of this concept that ice floats. But what's interesting here is this latent energy. This ability that water can absorb a lot of heat before it changes phase. Now, to understand that, we have to draw a graph. It's probably your arch nemesis is a graph, right? So this is added temperature, change in energy, in heat energy. And here, and here's temperature. I'm trying to remember off the top of my head. And right now, this is for water. I could Google it, but I shouldn't have to. So. Yes, this is Celsius. This is degrees Celsius. This is for water. This is for these are molecules of water, a sample of water. Now, if this is 0 degrees Celsius, and let's say this is 100 degrees Celsius, and this is 200 degrees Celsius, and this is 300, and this is 400. Let's start with water being here at somewhere, let's say they say this is negative 100. This water is really cold. What happens as we start here below zero? What happens as you increase heat, as you keep increasing heat? Say that again? More kinetic energy. What happens to the temperature? It keeps going up. Do you agree that this would go something like that? Now, normally, if I had time, we would have done a lab, and I would have. That's one of the. I love this lab because we have these little probes that we can stick in there. When I was a kid, we had to stick the thermometer in and keep measuring every 2 seconds or 5 seconds. Actually, it was 30 seconds, I think. We would measure every 30 seconds the temperature. As the temperature kept rising, we plot our points. We plot a point here and here and here, connect the dots, and we see it was a straight line. Well, you have these machines that connect to your TI-84s or 85s, and they're probes, they're temperature probes that'll actually measure every 2 seconds or 3 seconds, and it'll plot the points for you. It's pretty cool. We don't have time to do it though. But an interesting thing happens at zero. Does anybody know what happens at zero?
At 0 degrees Celsius?
All right, so I'm going to draw it. At 0 degrees Celsius, this happens. You keep adding heat, and it doesn't change. The temperature doesn't change. Well, we're going up, so it's not freezing. What's it doing? Temperature's going up. What happens? Do you understand that it's solid down here, right? It's turning to liquid, so what's that called? It's not freezing. It's melting. It's melting. All right, so fine, we're at zero. And it's going to stay at zero for a while, even though I keep adding heat. But then all of a sudden it starts to go up again. It's still liquid. This solid, down here it's solid. Down here it's solid. Up here it's liquid. Yeah, that's the question. So it's going to keep going up. Temperature's going up. The thermometer is reading hotter and hotter as I increase heat. That makes sense. That part makes sense. I keep adding heat, it gets hotter. But duh. That's not a question. The question is what's happening at when we reach a certain point?
It turns to a gas.
It's turning into a gas, but why isn't the temperature increasing? It doesn't increase. You're adding energy to move it, but it's not increased. And then all of a sudden, at some point, you keep adding heat, and it just goes up, and it keeps going up, and it can get up to 1,000 degrees. So this is what. Give me a second. These are good guesses, but let me write it down. This is when it's a gas. Oh, by the way, I guess I should tell you there's another point as well. At some point, and I don't know what temperature it is, but there's another latency. This is called latency, right? It doesn't change. And you get another form called plasma. Huh? Is it time to go? 4 more minutes? Okay, good. Yeah, question?
So the 0 point, when it's not changing its state, would that correlate with water size specific heat? Because it's really hard to change the state of water.
That's right. This is the specific heat. This is what the measure. The higher the specific heat, the longer these lines are. The more energy you need to change phase. That's what specific heat means, right? So the question is why? Why does water have such a long latency period, right? Why does water have that large specific heat? Water, H2O, has a capacity to absorb a lot of heat. It's very hard to melt the ice in Lake Erie. That water stays cold well into May before it starts to really warm up enough for us to go swimming in it comfortably. It stays liquid well into the winter. And the ocean rarely freezes off the Pacific and the Atlantic. Large specific heat. The question is why? What is stopping the temperature from increasing? Yes, that's right. Hydrogen bonds. You have to use that energy to break the hydrogen bonds first. You have to use that energy to break the hydrogen bonds before you can change it into liquid. The temperature can't increase because every time you add energy, it goes to breaking those hydrogen bonds. And there's so many of them that it takes, of course, the more you have, the higher the more energy you need to change the temperature to melt it. So the larger the block of ice, the more energy you need to melt it. But by the way, the entire thing has to melt before the whole thing can increase in temperature. So if you have a glass of ice water, until all the ice is melted, the temperature will be 0 degrees. That is 0 degrees Celsius on average. Obviously, there's going to be warm spots and cold spots. But on average, it's 0 degrees Celsius until all the ice is melted. It cannot change temperature until all the ice is melted. So you have to have, this is called phase change energy. Phase change energy. And that was another question that was asked of me. Over email. And I hope that answered it. So that's the other reason that's another great thing about water. It stabilizes the large bodies of water, stabilizes our temperatures. It makes Cleveland, believe it or not, very stable as compared to Columbus. It gets much colder in Columbus and much hotter in Columbus than it does in Cleveland. Same with all along the coast and the island. If you look at the deserts in the middle of the continents, they get much hotter, or the frozen tundra of the north, they get much colder than the places near the ocean. The places near the ocean can stay much more stable temperature because of this. And it's also one of the reasons we're not all dead from climate change, global climate change too, because a lot of the heat is being absorbed by the oceans. All right, so I'll take attendance on my own. Have a good one.
On your own.
Meaning I won't wait. You don't have to wait for me. I know who's here. So.